Hi everybody, welcome to Florida Polytechnic University's Google Hangout STEM Talks. Today we will be talking about debunking pop culture myths from core science facts. My name is Richard Troncalli. I am the social media coordinator from Florida Polytechnic. And so right now we have today three professors from our university. First one is Dr. Thanos Gentimus.
Hello everybody, my name is Thanos Gentimus. I'm an assistant professor here at Florida Poly. I do mathematics and analytics. My focus is big data analytics and all things involved around that. I teach calculus 1 and differential equations, and I'm really happy to be here.
Thank you, Dr. Gentimus. Second, we have Dr. David Foster.
Hi, I'm Dr. David Foster. I've been at Florida Polytechnic about 6 months. I've been in computer engineering for a long time. I also have a background in electrical engineering with a little bit of physics and math thrown in for good measure.
Well, welcome. And last, we have our assistant professor of chemistry, Dr. Jaspreet Dow.
Hi everybody, this is Jaspreet Dow. I'm assistant professor of chemistry. I teach chemistry here, but I also teach intellectual property right management. My area of research is solar thermal storage. So I develop technologies for storing solar energy in the form of heat so that we can generate electricity when sun is not available. Let's go.
Great. Okay, so our just so everyone can know for the audience is if you have any questions, please feel free to ask them at any time. So the first question we want to get us started is about The Martian, a movie with Matt Damon who is stuck in Mars and who grows crops. So really for Dr. Dow, can you really grow crops on Mars?
Yeah, so I won't give a direct answer to yes or no. I'll just try to a little bit explain that. So if you're just thinking of taking seeds from Earth and going to Mars and putting that in the soil and thinking that plant will grow, the answer is no. But can we grow it if we can control certain aspects related to growing the plants on the Mars? The answer is yes. What is those things? So when I look into what are the conditions which are needed for a plant, for a seed to germinate and the plant to grow, so there is a soil. We need the right soil with the right nutrient because every plant need the nutrient to grow. So are there those nutrients available in the soil of Mars? The answer is yes. The nutrients are available like calcium, sodium, potassium, zinc, magnesium. Those nutrients are in there. So there's a check mark there. Yes, we can do that. The second is, as we all know, the atmosphere on Mars is very thin. The air density is very low. So as a result, Mars gets a lot of radiation. And we are lucky on the Earth that we have a very thick blanket of atmosphere on the top of us, which protect us from harmful radiations, which protects the plants on the Earth. So how do we go around in Mars? So that's well shown in the movie, although they didn't intend to do that way. But they had this station which protected the astronauts from the harmful radiations. They were moving freely without the spacesuit and all that. So you can use that as a greenhouse, which can protect the plants from the radiations. Then, for a plant to grow in a soil, the soil needs to have a certain microbial diversity. That means it should have microbes in it.
Well, so how do you get those up there? I thought that Mars didn't have any microbes, and I think in the movie didn't they use human waste? Is that a little bit of a problem, right? I mean, there are all sorts of pathogens in there, right?
Yeah, and frankly speaking, right now, if I say, okay, are there no microbes available in the soil of Mars? We didn't get a direct evidence, but I won't rule it out because microbes are known to if water is around, they're known to flourish, they're known to grow and divide in very, very adverse conditions. So right now, probably we don't have that evidence for that. Yes, what is shown in the movie is that there are not microbes available, so what this guy gentleman did was to use human waste. And using it directly will be a problem because different persons have different pathogens, different microbes, and that may cause some problems, some contamination. So human waste needs to be treated to make it suitable as a manure. And on Earth, it happens naturally. The human waste or the animal waste, the way the microbes are, they work on it and convert it into a useful manure. So on Mars, how you're going to do it? One way, and the research is there, is treating those human waste with radiation so that you can convert that into a useful manure. You can do that. So as far as the microbial diversity is concerned, we can work around that. But the biggest hurdle which could come from some of the things which are there in the soil, which may be toxic, toxic to the plant, and toxic to human also. And that major chemical which may be responsible is the perchlorate. And the perchlorate is a very unique molecule, and it's a molecular ion. It has a negative charge associated with it, and it is present on the soil in the form of calcium perchlorate. And the water, we say water on Mars is not available as it is available on the Earth. It's available in a very concentrated form. It's actually a very concentrated brine, and it has a very high concentration of calcium chlorate. Because the physical properties of the calcium chlorate allows it to dissolve into water to a very large extent. So calcium chlorate, I have brought this model here. This is the chlorate ion. In chlorate ion, you have a calcium in the middle, and there are 4 oxygen atoms which are directly linked to the chlorine, in fact, not calcium. This is chlorine here. And there is a negative charge which is uniformly dispersed on all the 4 oxygen atoms. So that makes this ion very, very stable. So when you dissolve this ion in any solvent, even in a solvent with a very low dielectric constant, it gets completely dissociated. So you have the metal ion and you have the chlorate ion. Metal ion, most of the metal ions, they're heavily hydrated and they have a high hydration energy. But as far as the chlorate ion is concerned, because it's a big molecule, it has a very low negative charge density. And that's the reason it is weakly hydrated and it has a very low hydration energy. So that makes it a very, very a unique molecule. On Earth also, we have some areas where we are dealing with high concentration of perchlorate in the natural aquifer, which is toxic. So we need to tackle this issue if we want to use Mars soil for growing, well, the plants.
So right now, it would be impossible, but is there a way to, for instance, draw it out and maybe even use it? Because I remember you were telling me that it's actually a useful, chemical compound if you treat it right.
Yeah. So perchlorate, one of the advantages, the life needs oxygen, is right? So this is a molecule which has 4 oxygen atoms. So it's oxygen rich. That makes it a very, very powerful oxidizing agent. So when you just think in a normal way, that you bring an oxidizing agent and a reducing agent, yes, they need to react spontaneously, and it will be a big kind of an explosion in there. A large amount of energy will be released, but that doesn't happen with chlorate. Chlorate doesn't immediately react with any of the reducing agent and give the constituent elements out. Thermodynamically, this reaction is feasible, it's spontaneous, but it's kinetically, this reaction is a very, very slow reaction. So when I talk about kinetically, that means the activation energy is really high. So you need to develop an alternate pathway for the reaction where you can decrease the alternate energy. So how you can do it? By using a catalyst. So there is a chemical way of getting rid of this chemical. So you can use a catalyst which decreases the activation energy, and you can reduce the perchlorate into, say, one of the product could be the oxygen molecule, and the other could be a chlorine and some other constituent species. And HCl could be also a byproduct of this reaction. But as I said, it's a very, very slow reaction. The other is the microbial. Microbial has a unique advantage. So if you can't take microbes with you, or if you can have those microbes in the human waste, and that microbes in the presence of, again, some kind of a catalyst can reduce this perchlorate into its constituent elements. Nanotechnology is another very good way of getting rid of perchlorate. I recently read an article where the nanoparticles, the iron nanoparticles, has been found to be more than 2 times efficient in decomposing perchlorate into its constituent elements. And perchlorate could be, if we could find a right combination, perchlorate could be a source for getting fresh water for irrigating those crops. So this is a kind of a blessing in disguise. Yes, it's a problem. It's posed a problem. Can we solve this problem? The answer is yes. So once we solve this problem, there are other uses which we can get from the perchlorate. So to answer your question, we can grow crop on the Mars. They are being studied, being done on NASA scale, where the crops have been grown in the space station. And one more thing which I'd like to, since we begin with this Martian movie, the reaction which this guy did to produce water, and the explosion which happened.
The explosion was interesting, right?
Yeah, it was interesting, but I actually saw this movie twice, just for that simple reason. What happened? Why this explosion? 2 times. So there was 2-time explosion. Why this explosion happened? So the reason which was given in the movie said that this guy didn't take into consideration the oxygen he is exhaling. Guys, we don't exhale oxygen. Yes, there will be some amount of an oxygen, but this is a closed environment, okay? So you're exhaling, you first inhale oxygen, what you're exhaling is carbon dioxide. So the amount of oxygen won't change because you are exhaling.
It's actually going to go down, right?
It's going to go down. The second explosion is very interesting, and probably tell me if I'm wrong. It doesn't talk about why the explosion happened. Could be due to the respiration, not the respiration by this gentleman. The respiration because of the plants in there, because of the photosynthesis. It
gives out oxygen, right?
It produces, not the respiration of the plant. Sorry about that. It's the photosynthesis of the plants. The photosynthesis process produces oxygen. So he didn't take into consideration when you have too many plants in that closed environment, the oxygen amount is going to go up, and that may cause some problem as an explosion.
So I wanted to follow up with you guys on the next question that we had was, why does it take so long to get to Mars? And Dr. Gentimus, can you just elaborate on that one?
I mean, the answer is very, very simple, right? The distance from Earth to Mars is 55 million kilometers. That's quite far. I mean, imagine driving with your car 70 miles per hour. It would take you at about 29,000 days to reach Mars. And we're talking about the closest distance, right? So I have here 3D printed versions of the Earth and Mars, right? So at their closest stage, 55 million. But remember, these two things rotate around the sun, all right? Actually, they should be rotating this way. And so at their furthest, they could be all the way to 400 million kilometers, right? And on an average, the distance as they travel through space is at about 200 million kilometers. So it's quite far. Even a big spaceship like Hermes, it would take it a long, long time to get from here to there. And that is if it was going in a straight line. But here's the idea. It's not going in a straight line, right? Because all of them are moving at the same time. So Christine, can you help me here a little bit? Okay, so we have Earth and Mars. Christine is going to demonstrate now. They're moving around the sun. Let's suppose that the sun is sitting over there, and they're moving around the sun. So if you wanted to go from one of them to the other, you're not going to go, for instance, you're not going to go here in a straight line, because as you're moving along, these guys are moving also with you. So if you were pointing at Mars when it is at the moment that you left, you're not going to find it there. It's going to have moved away. So what they do is they create specific orbits, pulsar orbits they're called, that go around and they meet the object where it is going to be when you reach it. The idea behind the Hermes is it's never going to lift off the Earth. But what is it going to do? Is it going to be rotating a little bit around the Earth, then travel to Mars, rotate around Mars, and then come back. Okay? So, by the way, this is somewhat an elaborate differential equation system. You could theoretically solve it, but if you've seen the movie, the guy that comes up with the beautiful orbit had to actually use a supercomputer and feed all the data in there and just do the numerical approximation, because we have a three-body problem, there are other elements floating around here, and somehow we need to figure out how to go from here to there. Everything's rotating, everything's moving. That's why it takes like so long to go from one place to the other. Now, I wanted to mention something else as well. They say in the movie that they perform the Parnell maneuver. That's basically when you are trying to use the Earth's gravity to slingshot around and come back the other way. So they weren't really trying to turn the vehicle around and go backwards. No, they were trying to use this thing to slingshot around and try to meet it at the orbit where Mars would be after so many months or so many years, whatever it was. Okay? And the interesting thing about this, the technology exists. I mean, the ion drives, the ones that are used by the Hermes, exist on a small scale, of course, right? So the idea is you have gas being sucked in and turned into ionized and spit out. The acceleration is very, very small. It's something like 2 meters per second per second. But imagine this traveling from one to the other, almost constantly accelerating. There is no need also for it to lift off the one planet and go to the other one. That is achieved by they passed by, and they have the map, as they said in the movie, that will go from the Mars into the spaceship. This one grabs it and goes back. And then when you reach there, you go back from the Hermes down to the Earth and vice versa. Remember that they used that rocket, that Chinese rocket, eventually they used it to resupply the Hermes. This one never stopped. It just went around the Earth and flew and found the other orbit of Mars.
So that's how they ensure that the Hermes is lighter. Probably if they don't do that, then they need to carry a lot of fuel.
Yeah, that's exactly right. So David was telling me there is some sort of crazy ratio about how much fuel you need in pounds in order to move that many pounds of useful carriage. What I wanted to mention.
I thought it was like for every pound of fuel you needed to land on Mars, it took 10 pounds of fuel to get it out of Earth's gravity world.
Right, right. But if you think about the Hermes, which by the way is an ancient Greek god that zipped around using magical flying sandals, all right, and it's very, very fitting because it was going to Mars, Ares, which is again ancient Greek mythology here. So the idea was for Hermes never to land, just to go that trip around and around. All the missions were created in such a way so that it never really stops, and that saves all that fuel to lift things from the Earth and send it there.
And probably the benefit, it never enters into any of those atmosphere, rather, means the Earth atmosphere or something, is that right?
Actually, in the book, it is explained that it does do that a little bit because that's how it sucks in the chemicals that it needs to ionize. So it really sucks a little bit of the atmosphere of each planet, but not too much. It just goes on the fringes.
The reason I'm thinking is probably that's how means the material which is for this Hermes is the friction is not there. So probably the degradation in the material is not. So that's the other advantage, that the degradation of the material is not that much.
And to give you also an idea, we have sent a bunch of things up to Mars by now. But for instance, the Mariners, which were some rockets, basically think of them as a rocket with a computer on top. We're not talking about the scale or size of the Hermes. Those took at about 140 to 200 days to get there. We had some space missions back in the 1976, the Vikings. That was like 300 and something days. The fastest thing there, I believe it was one of the Mariners that was 130 days. But imagine now, these were basically a rocket and a little bit of a computer on it. The Hermes is huge. It's gigantic. It's like, I don't know, it's a 10 orders of magnitude bigger. I'm exaggerating here. It's a lot of orders of magnitude bigger than the space station that we have right now. And imagine moving that thing left and right, carrying all the people in there, having the rotating thing. That's kind of impossible. But still, I want to point out, theoretically, it is doable. Okay, the technology is out there. Those iron drives exist. It's just that they wouldn't be able to move something that huge very efficiently. You still need a lot of power, which we don't have right now.
Well, thank you, Dr. Genthimus, for that one. So I wanted to just jump ahead and just go over the next topic that we had, which really involved the Back to the Future. And thanks to the DeLorean, we have a lot of people now who want to know if they can fly a car. So the question I want to shoot over to Dr. Foster is, why do we not have flying cars yet?
Well, the answer is that we sort of do. There have been flying car prototypes being created for the last several decades. There's a company that supposedly is going to make a flying car commercially available next year. It's not going to be cheap. It's going to make a Tesla look fairly economical. But there are a number of engineering challenges to start with. If you need
to put we have helicopters. Isn't that what we're looking for here?
Yeah, we'll get there. I mean, the Back to the Future, it just lifts up off the ground and flies away. If you're going to lift something that's 3,000 pounds, which is about what a normal sedan weighs, you're going to push a lot of air down, blow over trash cans. That's not something you're going to use in the driveway of your house or in a parking lot. If you want to spend a lot of money to make it light, you're using composite materials, aluminum, titanium. I mean, not the steel that they use in a car. So maybe you can get that 3,000 pounds down closer to the 700 pounds of a two-person personal aircraft. You're still creating a giant disturbance, and we just don't have the infrastructure for places to take off and land in that vertical takeoff and landing situation. Watch a helicopter land in a war movie, or watch a Harrier jet. I remember True Lies. True Lies. Arnold Schwarzenegger jumps in a Harrier and takes off, and he's blowing over cars and doing all kinds of damage. That's the kind of effect you would get if you need to launch a car off of the ground. Yeah. And then there's the human element. Give us 17-year-olds have a neck problem right now. Just navigating 2 dimensions and trying to dodge people is an issue. As soon as you get something above 55 pounds, the FAA becomes involved and says you need a pilot's license, you need to start talking to towers, we need to make sure that all these things are not constrained by roads or not randomly flying into one another. And now that you're moving in 3-dimensional space, instead of just accidentally bumping into somebody's garage door, you can land on their roof, you can land in their pool. You can do all kinds of irresponsible damage. So you would need pilot's licenses and all kinds of training to be allowed to operate one of these if you could afford it.
So tell me about, maintenance. Wouldn't that be
Commercial aircraft have teams of people that look at them every time they touch the ground. The pilot does a walk around. Most people don't maintain their cars at that kind of level. If you want to get into the mindset, for the next week, every time you walk out to your car, check the tire pressure, open up the hood, check your belts, check your windshield wiper fluid, check every fluid. And if
I don't think I would be doing that. Sorry, David.
No, I did it once, and that was enough. I think it was 19.
And fuel is only $1.70 right now, so that would help too.
One thing is also means person on the ground and a person in air is different. The physiology, the chemistry is different. So it will be difficult. It's not like a normal skill you need.
That's right. Not all of us are born pilots. Is that what you mean?
Yeah.
Yeah. And even then, even though it feels like a cool thing to do, it's not that useful. The automotive companies have been focusing recently on making cars more fuel efficient, which is why we have the Nissan Leaf, the Toyota Prius, the Chevrolet Volt. A lot of cars come in hybrid forms now, and that's to maximize the number of kilometers we can move a person per kilogram of fuel. Cars, we can make electrical, charge them up with any source, solar power, nuclear power. Every aircraft that's commercially flown uses fossil fuels. Mm-hmm. And there is no plan to ever turn an airplane into an electric vehicle because we cannot get a battery that light. I mean, lithium-ion batteries are fine for the little quadcopters you can buy in an RC store, by the time you scale it to something large enough to carry people, it's far too heavy an aircraft to be viable.
So we're missing the source. Is that what you mean?
We're missing the energy. We don't have the energy to drive an electrical airplane other than something with
fossil fuels, maybe.
Wings of solar panels that looks more like a glider that can barely keep itself in air. But it's nothing you're going to use to move cargo or to move hundreds of people at a time with anything that's on the horizon.
So unless we invent anti-gravity, no flying cars, right?
That's pretty much it. That's pretty much it.
Well, thank you, Dr. Foster. And so I also wanted to talk about the Fast and the Furious. And Donos,
Sure.
so was the dragging of the vault really possible?
I mean, Richard, no. That is quite impossible. I mean, in the back here, I wrote a derivation, and I was actually here, if you can see. I wanted to just go through it, but then I was like, no, I'm just going to state some facts and let you guys figure it out on your own. The vault, supposedly, is at about 9 tons, like 9,100 kilograms. And they are stealing $100 million, which that comes about, I mean, stacks of 20s, that comes about to, like, I don't know, 4 tons also. So we're talking about a combined mass of something between 12 to 15 tons, okay? And we're pulling them around with 2 cars, which I did the math here. Those cars can produce 425 watts of power, okay? And we have 2 of them. Excellent. Let's think that there's no friction, okay? I'm giving you that. There's absolutely no friction. This vault is sitting on this perfect gliding thing. There's absolutely no friction, which we all know that that's not true. But even if there's no friction, they show in the movie that within 15 seconds, the cars start and they pull the vault behind them going 50 miles per hour. Yeah, okay. So if you do the math, which is behind me, it's a very, very simple equation. Just equate the 2 energies. And again, no friction. You're not killing any friction here. After 15 seconds, those 2 cars would manage to pull the vault with a whopping speed of 2.312 miles per hour.
Which is not a quick walk from an
That's exactly. You would see old ladies passing them by. It's like, hi, what are you doing stealing that vault?
No, don't kill it. I was thinking there was $100 million. You're telling there was no $100 million in that vault?
I mean, even without the $100 million, we still cannot make 50. It's absolutely impossible. As a matter of fact, if you want to reach the 50 miles per hour within 15 seconds, you need to be pulling the vault. Are you ready? With 476 similar cars. You heard me right. 476 of them, not just 2. Right? And besides that, there are all sorts of problems, right? Right, David?
Well, yeah, number one, $100 million split 476 ways isn't worth the job.
No, I need my money back. I need my ticket back.
That's not science, right?
But even if you got the safe moving at 50 miles per hour, they show this chase scene where they turn corners and the vault just swings around and goes through banks. And the image that went through my head is imagine a 200-pound man jogging down the street with a little chihuahua running in front of him, and that chihuahua sees a lizard or a squirrel off to the side and goes chasing after it. It's not the 200-pound guy that gets flipped on his back. I mean, that dog gets drugged behind the guy. Once that safe gets up to speed, if you took the 30 minutes or whatever it took to accelerate to 50 miles per hour, that safe has inertia. And you need just as much time with the cars pulling in the opposite direction to stop that inertia. So when those cars turn the corner, that safe is going to go on without them and just drag them along behind.
That's right. That's right. So, and again, we're assuming everything without friction. Friction would totally kill the argument, all right? We have this huge vault with a huge surface area. Remember, friction grows by the surface area. So imagine this huge surface area and this huge vault sitting. To even start it off, it would be close to impossible if we are thinking that it's not gliding on wheels, which, by the way, if you watch the how-to of the movie, it was gliding on wheels to actually make the scene happen, because it is literally impossible to move something like that with or without the 100 million. Just breathe.
Probably a styrofoam safe on wheels.
That's probably true. But yeah, no, that really cannot happen. It's impossible. It is impossible to move.
I'm just thinking the heat. Means if there is a friction, just think about the heat. What kind of a material this vault is made up of? That it can sustain the heat in them. And so I'm just it melts, and if there is $100 million, man, they're going to catch fire.
Well, that looks like we're ready to wrap it up, and I want to thank all three of you today for our STEM Talks discussion, and so definitely appreciate it, and for the audience, thank you guys for listening tonight as well.